Today at Unreal Fest Online 2020, we'll be doing a deep dive into our cross-platform build farm. Hi, I'm Adrian. At Boss Alien, I write backend software and look after our build farm.
Hi, I'm also at Boss Alien, and I've been looking at Unreal's build tools as part of my recent work.
Who is Boss Alien? We're a Natural Motion studio, part of the Zynga family. We've been making mobile games since 2011. You may recognize us from titles such as CSR and CSR Classics. Not too long ago, we had some pretty exciting news. We had a new project to work on. With a brand new game to build, it was time for us to evaluate game engines to find one that would fit our needs. And we're presenting here today, so no prizes for guessing which engine we settled on. It's been a good experience so far. Starting fresh on a new project gave us the opportunity to plan our build processes from the ground up, and that's what we'll talk about today. Before we go too far, who is this talk for? Software engineers who are building outside the editor for the first time, especially in projects which require engine modifications. And those who are new to build farm planning for Unreal, who would like to learn more about what to consider when assembling a build farm. So we'll cover off two topics today. Chris will look at the anatomy of a single build, how we utilize Unreal's build and testing tools. I'll zoom out and see what it looks like to do this build on many agents across a build farm. Over to Chris.
Before we dive into things in depth, I want to give you a quick run through of what we wanted to achieve as we started building this system, and how it guided the implementation. We knew that we'd have to support the game running on multiple platforms, including a Linux dedicated server platform, and we knew that we'd want to make engine changes to Unreal, meaning we'd need to build the engine as part of the normal build process. We also knew that iteration time would be a key part of working effectively as a team. Being able to get builds in people's hands to test new features is important to us, as we have a design through play philosophy. Conversely, we also knew that we'd want to be able to build things from scratch, as we didn't want to make release builds from an incremental, and to give us the peace of mind that the build is always buildable from source. Another goal was to be able to upload builds for easy access and distribution amongst the team, something that had been a win for us on a previous project. Experience on previous projects has also taught us the value of automated testing, something we wanted to integrate as much as possible in the build. I'll talk about this more later, but it's proved to be valuable. Finally, we felt that it was important to support these builds across multiple branches, as we knew that we'd have to support at least a release and a development branch simultaneously. I'd also like to give a quick overview of the two main pieces of third-party technology we use as part of the build. Jenkins, an automation server. This allows us to set up and monitor build jobs and agents. Adrian will go into more detail on how we use Jenkins later. We also use Perforce, which is our source control management software. It's supported as an SCM solution by Unreal out of the box, and offers useful features like being able to deal with large binary files and file locking, which helps avoid conflicts with binary assets such as blueprints. Perforce is the concept of a workspace. This defines what files to sync, as well as keeping the state of what files have been synced to disk. As part of achieving the goals we set, we aim to support a few different build types. Clean, which means from scratch. Everything is synced and the workspace on disk is cleared at the end. This was the first type of build we implemented, as our priority was to be able to make builds for our QA team. Soon after that, we worked on the continuous and incremental builds. They differ in that the files are not cleaned up after a build, so are much quicker to build. We wanted a continuous build running on our main development branch to confirm that the target builds on all platforms we require, to make sure we have as few broken build situations as possible. We also took the opportunity to use the continuous build to upload editor binaries to Unreal GameSync to cut down on the number of build jobs and to save disk space on the build machines. I'll go into more detail on how we use UGS later. The final build type we implemented is a nightly build. This runs every night and builds each of our target platforms from scratch, including shipping configurations. These are useful for checking any compile errors in shipping and to ensure things like iOS signing is working as expected for enterprise builds. We found it useful to surface any errors as quickly as possible, but we didn't want to overburden the machines we have by building this continuously. As you can see, we support shipping builds from clean only, as we don't use them from day to day, and changing configurations will cause an engine rebuild, something we want to avoid in our quicker continuous and incremental builds. So as we dive into the build itself, I'll go through the main steps clean and incremental builds take. Here's the clean build. I've made the length of each step proportional to the amount of time each step takes. First, we clean by deleting any existing files on disk and deleting the associated Perforce workspace if it's present. This should be very quick, as normally there's nothing to do, as we also run a clean at the end of the build, but we wanted to keep it to ensure working from a clean state. Then we sync, meaning we copy down the files at a specific revision from Perforce. Normally this is the head revision, but one can be supplied as part of the build parameters. Then we build any dependencies we need to build the game, such as the Unreal Editor, and then the game, or target, itself. As you can see, this takes up the majority of the build time. When that's completed successfully, we upload the target and symbol files to an Amazon S3 bucket for distribution among the team, or an editor for UGS, which I'll talk about later. Then we run our set of tests, and then delete the files on disk and the Perforce workspace. So now you can see the incremental build. The first thing to see is the time difference between the two. You can also see that the same steps are taken, except that the clean step is omitted. Uploading and testing takes the same amount of time, but the sync is usually much faster. We've kept the files on disk and the Perforce workspace, so we're only syncing any differences. The build itself is also much shorter, as the incremental build products are still present on disk. Now that we've gone through the main steps both build types go through, we'll go into a bit more detail on each step. So after a potential initial clean, the build needs to get the latest changes from Perforce. The number of changes may be large, especially if we're syncing from a clean state, and we need to make sure the appropriate Perforce workspace is being used and is also in the correct state. We'll also potentially need to do some further operations later on in the build, like checking out ini files or submitting editor binaries. To do all of this, we perform a number of steps in the build. The first thing we do is set up the correct Perforce settings to run further commands. We were running into problems trying to use Perforce commands as part of the build, as we found ourselves having to pass the current workspace user and credentials every time we wanted to check out a file or when Unreal submits a binary to UGS. This was making the build error prone, as some parts of the build we were trying to use the wrong settings or Perforce environments that had been wrongly set up beforehand. To avoid this problem, we now create a p4config file in the initial stage of the build. This file contains information on the correct user, workspace, and credentials to use for any Perforce operations under the folder the p4config file is created in, and is used automatically by any Perforce command line or API command. This means we don't have to worry about trying to pass any command line options or any misset environment variables for the rest of the build. Then we set up our Perforce workspace. We'll need one to sync the files to disk. We use the Perforce plugins for Jenkins to do this. We do a sync but a preview sync. This operation finds the correct workspace to use, or creates a new one if it's missing, but it doesn't sync any of the files to the workspace. Initially we used the plugin to sync to, but we found that we couldn't filter the set of sync files. This was syncing too much data that we didn't need for the build, slowing down the process. So now we directly call the p4 sync command, with extra options to enable parallel syncing to cut down the sync time even more. Perforce supports the concept of taking work in progress and saving it, similar to Git stash, but the work in progress can be shelved onto the Perforce server itself. We've used this to help with our workflow. After the sync, the build machines can unshelve a developer's work in progress and create any build we want to without the risk of checking in untested changes. This has been very useful for testing features and ensuring that the code compiles across multiple platforms early in the dev process. And we can even distribute these to the QA team for any extra testing a large change may need before committing. One snag we hit was file locking. If developers had a locked file checked out, the build machine couldn't unshelve it. Using an undocumented Perforce command, the exclusive locks can be bypassed. This works for us since the build machines will never submit any unshelved work and will always revert it at the end of the build. We've also been careful to only allow unshelving in builds that can't commit editor binaries to UGS. We wanted to make sure that no shelved content would be used as part of the editor builds that the team uses. Once syncing is complete, we start our build scripts. We built these in Python as we wanted a platform-agnostic way to start the build process and one that is more maintainable in shell scripts. The team is also familiar with Python, and so this seemed like a good fit. We use the same build scripts for our local workflow too, which gives us a single system to maintain. The first thing that the scripts do is build any required dependencies with UBT, and then the target itself with UAT. UBT is Unreal's build tool. It builds project files, game source. When building project files, UBT scans for module build files and creates a set of project files for the chosen build tool, like Visual Studio. When building game or tool source, it invokes the build tool with the project files it generated. We use the build scripts with UBT to build any required dependencies needed to build the target. Once the dependencies are built, we use UAT to build the target itself. UAT is the Unreal automation tool, and is used to simplify common Unreal build tasks like building the target, cooking content, and deploying to device. We use the build cook run command line argument alongside some other options that set up the platform and project folders. We use build cook run because it does the full build, cook, and packaging step. The run step is useful in our local workflow context and is skipped if no device is attached. You can also pass skip deploy to completely skip the step too. We also specify that the build is unattended and to skip building the editor. We've now completed the build phase. There's a cooked and packaged target to upload. Now that the build phase has completed, we start uploading the target. If it's not an editor build, we zip it and upload it to an Amazon S3 bucket using Amazon's command line tools and make an API call to our internal build access web service. The team can log onto this service and download the builds and symbols for each of the platforms. If it's an editor build, we want to use UGS, which I'll talk about now. To support our goal of quick iteration times, we wanted to implement a hassle-free way for artists and designers to be able to get the editor as part of their daily workflow, rather than having to deal with building it from source themselves. We looked into a couple of approaches, but UGS stood out as the best path forward for us. UGS is Unreal GameSync, consisting of a client and a server, which allows devs to use an editor without having to build it themselves. The build machines create Win64 editor builds, which are then zipped up and checked into Perforce using UAT. The client queries Perforce for builds and syncs to the right change list, as well as syncing to the editor binaries and unzipping them in the appropriate location. The UGS server is used to tag the availability of builds by the build scripts and can store extra metadata, such as comments, for each editor build. In order for coders to not have to sync the pre-compiled binaries, they are submitted to a separate stream where all editor binaries are kept in order to keep the sync time down for non-UGS users. To submit the binaries to Perforce, we use Unreal's build graph, which allows us to define a set of build steps in XML. An example that builds the tools and submits them to Perforce is included with the Unreal source. We modified that build graph to use the receipts generated from the builds we make with our build scripts, so that it doesn't rebuild the editor and tools before submitting them. This allows us to use the same build scripts as our normal builds and submit editor binaries as part of our CI builds, making sure we have a constant stream of binaries for devs to use. And as editor binaries can be quite large, we only store the previous 16 revisions in order to keep the Perforce depot size down. The number of revisions to keep is specified in the build graph itself. Once the uploading is complete, we begin the final testing phase of the build. We run a number of tests in editor to help us verify that the code and content are as correct as possible. If any tests fail, the build is marked as unstable, meaning it completed successfully but that problems were detected. As part of our goal towards automated testing, the first thing we did was turn on static analysis for our own code. Static analysis is the automated checking of code to surface common errors that aren't surfaced by the compiler, such as using uninitialized memory. We use static analysis to give us more confidence in the code we're writing. It's not a panacea, but it adds another layer of checking for correctness. In order to use static analysis, we modified the VC toolchain in the engine to use Visual Studio's Analyze option for non-engine code. Once the build is completed, we scan Unreal's build log for any static analysis warnings and mark the build as unstable if so. Another thing we found out as we started development is that it's easy for blueprint or code changes to cause another blueprint to fail to compile. Sometimes this was missed and committed to Perforce, causing bugs in the game. We wanted to get an automatic check that would compile all blueprints and surface any errors. To do this, we run an Unreal command to compile all blueprints, which comes with the engine. We check the output for any errors, and if there are, we mark the build as unstable. So static analysis of the C++ code and compiling the blueprints to check for errors are very useful, but they could only go so far in detecting errors, as many in-game issues are caused by errors that can't be detected by analyzing source code, such as logic errors. Another potential source of issues is regressions. Changes to add functionality or fix an issue can cause problems with existing code. To allow us to check these, we've created unit tests for our lower-level game systems. Unreal provides a test automation framework and allows you to create unit tests with the F-Automation Test base class, or using the Implement Simple Automation Test macro. When running the tests, Unreal will check the output and mark any warning or error logging as a test fail, which we pass in order to surface any problems and mark the build as unstable. Once we'd implemented the unit tests, we wanted to apply the same ideas to testing the interaction of systems, as it's easy for issues to crop up here. To do this, we use functional or integration tests. Unreal's automation framework also provides a way to do this, using the functional test blueprint library. We create a map for each of the tests, which then include the appropriate actors and blueprints to set up and check for a positive result. We can then test the interaction of game systems. Although functional tests can be very useful, we need to be careful when creating the tests to ensure that they're reliable. If they're not 100% reliable, then they're worse than having no test, as false positives mean you can't tell if there's a real issue or not. We run both the unit and functional tests by using a Python script that invokes the Unreal editor with the alteration run test commandlet, then scans the generated report for any test failures. We start the editor with no video output and the unattended flag. We can also supply an FPS setting along to Unreal, which dictates the frame rate that the tests run at. It's important to be able to run tests at a range so that any frame rate dependent errors can be caught. They're often one of the hardest issues to track down, especially across a range of target platforms. Once the tests have been run, we hit the last stage of the build, cleaning. For all builds, we revert any checked out or unshelved files. Using the -W option, any files added via unshelving will be deleted too. If this is an incremental or continuous build, the build will end here, keeping the Perforce workspace and the files on disk ready to be used for next time. For clean builds, we delete the Perforce workspace, and then delete the files on disk. And that's it. The build is completed.
Now that Chris has shown us what a single build looks like, let's see how we do many of these concurrently. We'll need a cluster of servers, a build farm as we call it. I'm going to take you through how we planned our farm, what it looks like now, and how we monitor it. Before we could get started, we had to answer these questions. I'll go through them one at a time. To figure out what operating systems we needed, we need to know what binaries we're building. Being a mobile game developer, iOS and Android are the obvious ones. As Chris covered, we build the editor and store it in UGS. We need a Linux server as well. Like any software project, we have other servers to be built and utility scripts to run. We won't go into these, but I'll just say that it is immensely useful to have every job for our project being built from the same system. So now we know what our target binaries are. What platforms can these be built on? We can build Android from any platform. Our server, we build natively on Linux or cross-compile from Windows using Unreal's Clang toolchain. The Windows editor must be built from Windows. iOS must be built from macOS. Our non-Unreal build jobs could be run from anywhere. So we started to narrow down our options. We wanted to simplify the pathways a build could take. We consolidated our platforms. This was our result. Most Unreal builds take place on Windows, with the exception of iOS, which we do on a Mac. The rest run on Linux. We know how we will be using different operating systems now. Next, when do the builds run? And how many builds will we really need to do? Let's put our builds on a graph. On the x-axis, we have the time of day that a build occurs. On the y-axis, we have the number of concurrent builds which we desire at that point in time. We have our three build types: clean, incremental, and continuous incremental. So we build throughout the day. We have our clean builds. These are the full builds from scratch, including the engine build. We run an overnightly on all targets. A developer could kick off a build during the day, for example, and QA may want at least one build at the end of the day for the next day's playtest. Then we have our incremental builds. This could happen if a developer wants to verify that their build compiles on another platform, or QA may really quickly want to get a build onto a device to test out a specific feature. Finally, we have our CI job. We continuously monitor our repo, and a build starts if there has been a change on the stream. Given we have changes happening all the time, this does mean in business hours we are constantly doing incremental builds. One thing I'll mention is that unlike other build jobs, we only trigger one concurrent CI build per stream at any one time. These examples were just for one stream. If we have an active release stream where developers are making changes and QA is testing, we will effectively be doubling this requirement. And so on again for every additional stream we may have in use. So on this diagram, one of these boxes represents a single build. And it's worth noting that the width of each box here is representing the length of time that build will take to occur. But each build is really a number of targets, the targets which we showed previously. So looking at all the builds we run, it actually gets pretty busy when we break these builds down into the sub-targets which they are actually building. So now if we look at the y-axis, we see that we do have to do quite a few concurrent builds at any point in time. Now I've simplified things here to assume that we aren't queuing jobs, but for our CI or developer incremental jobs, we really don't want jobs to be queued for more than a few minutes anyway. Overnight, it probably doesn't matter so much if our clean builds have to wait an hour or two before they start. So without really going into the numbers, we see two things. The number of builds we need to do is huge, and there is a lot of variability in the number of concurrent executions of builds throughout the day. So answering this question at the top level, when do builds run? Well, throughout the day, but mostly during business hours. Our build agents, where are they going to live? You can self-host. This could be on a machine under your desk, in a server rack down the hall, or a rented rack across town. What are the advantages? Running your own machines, obviously you have full control, and you can have the exact configuration you'd like. Having build machines in your studio means networking and security are reasonably straightforward. By far the biggest advantage, though, is the return on investment. If you plan your hardware such that your machines have a high utilization rate and your project exists for more than a few months, you'll be reducing your budget in the long run with on-prem machines. Some disadvantages: a lot of upfront capacity planning to determine what you need to buy. And while there is some automation you can do with virtual machines, automated imaging, and remote configuration management, there is still going to be physical manual intervention required at certain points in time. IT support is going to be necessary to get these machines up and running and fixed when something goes wrong. Finally, waiting for machines to arrive, having them provisioned, and waiting for the inevitable repair process to occur will be time consuming. On the other hand, we can pay external vendors to run VMs on their machines, aka the cloud. We could use any of the major cloud providers: AWS EC2, Azure Virtual Machines, GCP. They all offer Windows and Linux virtual machines. And there are also some smaller providers who offer macOS machines. What are the upsides? Cloud machines are fast to spin up and down, and we can pay for them in short increments, by the month, hour, by the minute. This is useful for inconsistent loads. We could turn on 10 machines at 9 a.m. and turn them off at 6 p.m. Or even being more extreme, we could turn on a Linux machine for just a couple of minutes while it runs a job. Having no minimum time commitments means that we can easily test different configurations. Even if you don't end up using the cloud for your agents, this can be a good way to decide what on-prem machines you might want to spec. It's reasonably straightforward to automate both building and provisioning of these machines. We can use infrastructure as code tools such as Terraform and Packer. With a handful of scripts, we can prepare a Windows image which will boot up with Android tools, the Visual Studio build chain, Unreal Clang tools, and a Perforce client ready to go. On the downside, cloud providers are going to be expensive for long-running VMs. We can reduce this hit by locking in longer leases, paying by the year rather than by the hour. It's still going to be a big line item in your budget though, and we do lose some flexibility doing that. Additionally, if you aren't already operating some services in the cloud, migrating agents to the cloud can complicate infrastructure and security considerably. So, where these run, cloud and on-prem, we decided on a hybrid approach, which you'll soon see. Finally, what tool do we use to control all of this? Continuous integration and testing has been around for a long time, and more recently it's seen much wider adoption. There exist mature solutions as well as slick new tools. What we found was that many of these newer tools were not necessarily appropriate for C++ game development. They make assumptions about build sizes, durations, and assume builds can always start from scratch. So what did we need? Being scriptable, the ability to self-host, and multi-user access. This was common to most systems. Less common was P4 support, specifically supporting continuous integration of a set of various P4 streams. As you saw previously, we are going to need to run many agents. Ideally, the system will start and stop these agents automatically. Jenkins satisfied our needs. While the vanilla version doesn't cover every base, it gives us Jenkins files, a GroovyScript-based scriptable approach for defining custom build pipelines. Jenkins has some very useful plugins, notably the Perforce plugin, allowing us to run multi-stream CI jobs off our P4 depot, and the EC2 Fleet plugin for Linux, giving us dynamic Linux agents on AWS with very little work required. While those are some useful plugins, there are many plugins out there which are unmaintained, insecure, or both. We usually find ourselves keeping the majority of our build logic inside Python scripts, which we call from our Jenkins files. With Jenkins confirmed, we had enough information to put it all together. I'll take us through the current build farm configuration we have at Boss-Alien, with some notes about each of the parts along the way. We went with the best of both worlds, this hybrid infrastructure. Our Jenkins coordinator lives in the cloud. It's hosted on an Amazon EC2 C5 instance. Next are our cloud-based agents. Conceptually, these machines live next to our coordinator. Historically, this is where we started our implementation. As I mentioned, it's much easier to prototype systems in the cloud rather than with hardware which we may not yet possess. To our Linux agents. These are lightweight EC2 T2 small instances built on top of the Amazon Linux 2 image. We build the base image for this machine using Packer. The Jenkins EC2 Fleet plugin then does the rest of the work for us. It spins build agents up and down automatically. As the Linux startup and shutdown time is so fast, and we can pay by the minute, we typically let a Linux agent exist for the duration of just one job. Next, our Windows agents. These are activated when our on-prem agents, as you'll see later, are all busy. Like the Linux machines, we build our base image using Packer. Unlike the Linux VMs, however, these need to be much more powerful for an Unreal Engine build. On AWS, we found EC2 C5D9X large images to be effective for sub 1 hour builds. On AWS, we have to pay for these by the hour, so we don't turn them off immediately after use. Instead, we wait until the end of the current hour, and this gives them the chance to pick up any new build jobs which may land in the Jenkins queue. Next, we have our on-premises Windows servers. On each of our physical Windows servers, we have 2 Jenkins agents, isolated by VMware virtual machines. On these machines, a full rebuild takes around 1 hour, with incrementals taking around 20 minutes. Next up, we have our on-premises Mac Minis. These vary in age, but they are all similar in that they are running bare metal and provisioned with Puppet. A full rebuild on these is slow, around 3 to 5 hours. Fortunately, they are still decent at running incremental builds. If not too many source files have changed, the incremental build and test process again takes around 20 minutes. Apple updated their Mac Pro line in 2019. The rack-mounted versions fit nicely in with our Windows servers. The current lack of ESXi support means that we can't run VMware on these machines. So, like the Mac Mini agents, these are running on a native installation of macOS. Mac Pros do give us a nice speed bump over the Mac Minis, with 4 rebuilds down from 3 hours to 1. Given that clean builds are much faster on Mac Pros, but incremental builds are similar in time, we continue running our Mac Minis in our build farm. They run for incremental jobs, while the Mac Pros could pick up either an incremental or a full clean rebuild. So there you have our build machines and the coordinator. For the on-prem setup, we also have a Unreal-derived data cache, which is essentially a shared network drive which caches the assets which Unreal cooks. Finally, we run these servers in different physical locations, and our repo is quite large. So we have P4 edge servers in each location, effectively replicating our master P4 server in the same subnet as these build agents. This speeds up our checkout process as well as Windows agents putting editors which it has built back into UGS. Monitoring various metrics has been important during the development and day-to-day running of our build farm. We use a Jenkins plugin to send build times and build queue lengths to Datadog to identify negative build trends and bottlenecks. We graph our cloud instance usage over time. Once we implemented an algorithm to spawn new Windows build machines on demand, we wanted a quick reference to see how many were being used and when. This helped us with capacity planning when it came to purchasing our on-prem machines. Finally, we need up-to-date information about CPU, RAM, and hard drive usage across all of our build machines. This gives us a nice visual snapshot of how our system is being used and whether it is still meeting demand. Of course, we can't always be watching this, so we have alerts which are sent to Slack if nodes were to drop offline, have their hard drives approach capacity, or have their CPU usage spike for a prolonged period of time. Like any system, we are always identifying new areas of potential optimizations. Some top areas are streamlining our on-premises provisioning processes to be as seamless as our cloud-based solution, and moving additional builds to our macOS machines to ensure we maximize the usage of all on-prem hardware before bursting to cloud agents. One feature which was released after our build farm was designed, which we would like to investigate, is using the Unreal Build Agent. A beta of this tool was introduced in Unreal Engine 4.24. Using this on our agents will allow fast workspace switching and cleaning, and the propagation of errors and warnings to UGS. These features could likely simplify our build script and potentially help us squeeze more builds out of our existing build agents. So there you have an overview of our build process. We moved through things fairly quickly today, so I imagine there may be some questions. Chris and I will be around for the live Q&A after this presentation. Finally, you'll also be able to get in touch through email or Twitter via the details you see on screen. Thank you for watching.